Okay. So we're going towards the end of the semester. Next week, Monday is a working day. We're supposed to have a lecture. Tuesday is a holiday. So Monday is somehow sandwiched between holidays. Yeah, I'm thinking to have like a self-study period for that particular lecture. So Monday next week from 12 o'clock to 1:20. That's your self-study time for this course. Okay? But I see you on Wednesday. Next week. I even maybe assign something for you to do self-study. Maybe you work on your homework problems. Right? You will have lots of homework, so I will give the last set of homework today, and you work on your homework problem. So in the last lecture, we talked about the norms of a signal, norms of a system. So norms of a system are simply the norms of the impulse response. So eventually it turns into the norms of a signal. We define the three norms: infinite norm, one norm, and two norms. Okay, three norms. We see, sometimes pretty hard to compute those norms. If the signal is like complicated with a lot of sine, cosine, and exponential, all these things, computing the norm is kind of hard. Today I'm going to look at the computation of time domain two norm. It turns out that the two norm can be computed rather easily. If you try to compute one norm or infinite norm, it's indeed a quite difficult thing to do. Right? So that's why the computation of two norm is easy. So that's why we often use two norm in our study later on for optimization and things like that. Okay, see how we can compute two norm. We have a time function xt. Okay, xt is a time function. We wish to compute the two norm. Of course, we can compute two norm square. That's you can compute two norm square. Then we know how to compute two norm. So this is time function. Okay. We take the Laplace transform. See, a lot of things if you do it in the time domain is hard. After we take Laplace transform, things become easier. We take a Laplace transform. Okay. Suppose that this Laplace transform is a strictly proper. It's a strictly proper Laplace transform. It's a rational transform. It's a rational function. So the Laplace transform is like this. Okay. First of all, we make two assumptions. One is that this Laplace transform is a stable, meaning that the denominator has all the roots in the right hand side, in the left hand side of the complement. If this is more stable, then you see that this function, this time function, is going to go to infinity. If this function is going to go to infinity or persistent, for example, the step or something like that, or sinusoidal. In that case, of course, the two norm is infinity, it's unbounded, right? Because two norm is a square integral of the time function. The integral goes from 0 to infinity. So in order for this time function to have a finite two norm, it has to be, it has to be stable. The behavior has to be stable. That means when t goes to infinity, it has to converge to 0. So that's why we have to assume that this the Laplace transform all the poles are good poles. So that's one assumption. Another assumption is that we assume this is not really a transfunction. This is just like we assume that it's a Laplace transform of time domain signal. So this is just a Laplace transform. This is strictly proper. We assume it's strictly proper. Okay? You see that there's no A0. No, B0. You don't have B0. Strictly proper. Why we have to assume it's strictly proper? If it's not strictly proper, what we can say about this? If it's not strictly proper, then we know definitely in xt there is an impulse. Is that right? For example, if this is simply, if this is simply 1, suppose that this xs is constant. If this is constant, then of course this is impulse. Yeah. So if you have a constant term, if it's not strictly proper, that means you do partial fractional expansion, you actually have a constant term. That constant term will correspond to impulse in this xt. In xt, you have impulse, then the two norm is infinity. Two norm is infinity. Okay, we know that the two norm of impulse function is infinity. So again, in that case, there's no point to do any further computation. So that's why we only look at the case when this is strictly proper and this is stable, so that you really you have a finite two norm. Then you can do the computation, and the computation is sensible, right? Meaningful. How do you do the computation? You do the following. Okay, this is a Laplace transform of the time function. You need to construct the augmented Rouse table. This is a more than Rouse table, but it contains Rouse table. So this part is Rouse table. Okay? What you do is that you do the following. This part is Rouse table. It's from Rouse table of A, of this denominator polynomial. You do the standard way. A0 is here, A1, A2, A3, etc. Then you compute this row from these two rows, right? You do the usual thing. This product minus this product divided by this, you put it here. Okay? You complete the Rouse table. You complete the Rouse table because this is stable. You can indeed go into the very end. You know that all these numbers are positive. All these positive ones you can go very end. You won't see any negative numbers anyway. So all the numbers are. So this part is a Rouse table. From the Rouse table, you need to construct these two parts. Okay, look at the middle part. What you do is that you put a B1, B3, B5, B7 here in the first row. Okay. So from the numerator, okay? B1, you put B1 here, but not B2, B3, okay? B5, B7. Then you move this blue row to here. You just copy. You get two rows. Yeah. Then you follow the Rouse table rule to get the third row. Okay, basically this third row is from these two rows. You get that here. Using the same rule as rows table. Okay. After you do this, then you move this to here. Just copy it. Alright. After you copy this, then from these two rows, you generate the next row. After you generate the next row, then you copy one row to here. Okay, always copy in the same row. You know, you don't copy to there or there. Just copy directed from there. Or you say shift that, move that to this position. Okay, keep going until you run out of elements. Here what you do is that you take B2, B4, B6, B8. Okay, those are even number indexed B. Put it here as a second row. Okay, you don't put it in the top. You put it second row. Do that. Then you move this red row into this position. After you move to the position, you get two rows here. Then you can continue, get a third row. Third row again, follow the rows. After you get this, you move this one. This okay, those rows are always a blue, red, blue, red, blue, red. Actually, you know, you go. So the red one, okay, again, move it over and put it here. And then you from these two rows, you compute the next one. Okay, keep going. You keep going. Maybe this is not so accurate. So odd row. So because I thought it was 0. So this is considered as 0 row. First row, second row. Okay, you don't say first row, second row here. You say 0th row, first row, second row, third row. Then this red actually, those are actually even number. Right? So anyway, forget about this. It's hard to maybe there's a kind of confusion whether it's even or odd. But anyway, so you just follow this kind of procedure closely, and you should be able to get this table. So this table is called augmented rows table. So it goes beyond the rows table, right? These are rows tables here. Then from the numerator you get this. Now after you complete the rows table, then after you complete this table, let's try to get some numbers out. We have algorithm. We get the table, augmented rows table. Then we set alpha I to be the ratio of these two numbers. Where are these two numbers from? These two numbers are from the first column of the rows table. First column of the rows table. Okay. So those R's. So you see that the R, you have a 0 there, 0 there. That means that corresponds to the first, or say the 0th column. That's probably more accurate. Basically, it's from here. It's from here. See, all these guys are 0, 0, 0. So alpha 1. What is alpha 1? Alpha 1 is this divided by this. Let me see if I'm correct. No, actually, alpha 1 is this divided by this. Okay? This guy divided by this guy. Alpha 2 is this guy divided by this guy. Alpha 3 is this guy divided by this guy. Okay? From the ratios, you get all these alphas. Okay, alpha. Beta. Beta I is obtained from those ratios. Those ratios are again from the numbers in the first column of the middle part and the right part. So again, beta 1, what is beta 1? Beta 1 is this guy divided by this guy. Beta 2 is this guy divided by this guy. Beta 3 is this divided by this. Beta 4 is this divided by this. Okay, keep going until the end. You get those alpha and then beta. So alpha I is from the first column of the Rouse table. Beta I is from the first column of the middle part of the augmented Rouse table, or the left. No. This is the right part, the augmented part. After you get alpha I, beta I, you definitely have n of them, n alphas, n betas. Then the 2 norm is simply the square root of those guys. Right? You simply do this kind of simple computation. Make it 2 norm. Right? Let's look at the examples. The local transform of the alpha xt, the time function, is like this. We want to compute the 2 norm of xt. So you see from this the denominator, you have 1, 1, 3, 2, 1, right? 1, 1, 3, 2. From here, you say this product minus this product as a 3 minus 2, that's 1. 1 divided by this 1, you get a 1 here. To compute this, you simply move this down, because it's formed from here and there, but if you have missing thing, you put a 0 here, then you basically put this number here. You get this 1 and 1. Then from these 2 rows, you try to get this number. So this number is obtained by taking this product minus this product. 2 minus 1 is 1. Divide by this 1, you get 1. Okay? Then next, you compute this number, which is basically, you fill the 0 here, then you do the same thing, you get this 1. Or you simply move this 1 back to this position. Okay? So that's Rouse table. B 1, 5. You put it here, 1, 5. So this is B1, and this is B3. Notice that the leading term should be just 1 smaller than this. Okay. Right. Sometimes if you see a 0 here, if this 0 here, don't take this 2 and put it here. Right. If you have a 0 here, you don't have this term, then you have to make sure that the 0 goes here. Okay? So 1, 5, move these over to these positions. Then you say 1, 5, that's 5. Minus 2, what do you get? That's 3. 3 divided by this 1, it's 3 here. You get this 3, then you move this row over. With the over here, well, you have no way to continue, just stop. Okay? Because you have to get 2 numbers there, you have nothing here, just stop. So, this 2 and this 6 goes over there. Then 1, okay. Then you move this 1, 1. to this position. Then it says 6 minus 2 divided by 1, that's 4. Put it over there. After you get this 4, you move this over to here. So this one is actually moved from there. It's not from this kind of computation. Okay? Now, you complete the augmented round table. Now, in order to get the alpha, you do this. Alpha I is basically from here. This divided by this, you get alpha 1. Let me see. Okay. So you divide it downwards. Okay. So this is see, alpha 1 is alpha 0, 0 divided by alpha 1, 0. Alpha 0, 0 is that. This divided by this. Yeah. That was my mistake. This divided by this is alpha 1. This divided by this is alpha 2. So you see all the alphas are 1. So because you have 1, 1, 1, 1, 1 here. Right? Beta. Beta is this divided by this. That's beta 1. It's beta 1. Beta 2 is from here. It's this divided by this. That's 2. Beta 3 is this divided by this. That's 3. Beta 4 is this divided by this. Beta 4. Okay. So you see that now you get all the alphas and betas. They use the simple expression. Put those alphas and betas in. And the denominator is this is 2 alpha 1, 2 alpha 2, 2 alpha 3, 2 alpha 4. This is beta 1 square, beta 2 square, beta 3 square. And they add together, then you get this the 2 norm square of xt is equal to 15. Of course, if you just want to compute the 2 norm instead of 2 norm square, you just take a square root this side. Right? So the 2 norm of this xt is the square root of 15. Okay, so see, if we use this augmented round table, we'll be able to compute the 2 norm of a rather general time function. As long as you can take the Laplace transform, and the Laplace transform is a rational function, then you can go through this procedure to predict the 2 norm. Sometimes, if the Laplace transform is simple, it's just like a first order rational function, second order, third order rational function, we might just derive those formulas. So let's maybe look at this, these formulas and see. Maybe we prove one of them. Okay. So suppose that we have xt. So xt, the Laplace transform of xt is a third order rational function. is our general third order strictly proper rational function. So we wish to compute the xt, is the 2 norm of xt. Okay? That's what we want to compute. So we want to compute, then, we again follow the standard procedure. We form the rough table. Rough table is A0, A1, A2, A3. Alright. Then what is this? This is A1 times A2 minus this is A1, A2 minus A0, A3 divided by A1. That's the first element of this row, of the third row. Then you have another row. Another row is simply move this A3 down here. Right. So you see here, because you have a missing element, you put 0 there, then you need to get A3. So that's a round plot, round table. Okay. Then you try to get the augmented round table part. B1 goes here, B3 goes here. You move this over, A1, A3. Move this over. Okay. A1, A3, then from these 2 rows, you compute the next one. So this A1, B3, B1, A3, A1, B3 minus B1, A3 divided by A1. Number. I will get this number, A3 goes here. Move that into that position. So that's the middle block. The end block, B2. B2, you put it here. You don't have B4, so just you have only one B2 here. You only have B2 here, you move this over. You have that there. You move this over, then you cannot continue, then you stop. From here, you see alpha 1 is equal to this divided by this. Alpha 2 is this divided by this. It's A1 squared. A1, A2 minus A0, Alpha 3 is equal to this divided by this. A1, A2. Right? I get all the alphas. I get all the alphas, then there's a beta 1. Beta 1 is this divided by this. B1 over A1. Beta 2 is this divided by this. Beta 3, this divided by this. A1, B3 minus B1, A3, A1, A3. You get the order of and beta. So x t the 2 norm is equal to square root. You have a square root, big square root. Beta 1 square divided by 2 alpha 1. So B1 squared, A1 squared divided by 2 A0 1 plus beta 2 squared. So B2 squared, A1 squared, A1, A2 minus A0, A3. Two alpha 2. 2 A1 squared. Plus beta 3 squared, A1, B3 minus B1, A3 squared, A1 squared, A3 squared. Divide by 2 of these. 2 times A1, A2 minus A0, A3, A1, A3. So I get a rather complicated formula here. If I compare this formula with really the end, the final product I wish to have here, I still need to do some simplification, I guess. So here you see that I have a square root. I really don't like to see the square root. I put a square here in this side. I can remove the square root. What about that? Square root. In order to add all these 3 terms together, I need to find the common denominator, right? So common denominator. Actually, probably it's too early to talk about the common denominator. I probably have to do some sort of yeah. So let's change this first term a bit. First term is 2A0 A1 squared. B1 squared A1. Right? That's the first term. I don't want to see a lot of these fractions, too many fractions. So this is what? So you see that A1, A2 minus A0, A3, you can actually, you have square here, you have this thing here, you can cancel. Actually, oh, I can cancel a lot of things. Why? Oh, I forgot to cancel things here. So this is A1, this is A1 squared. That's good news. Right? For the second term, I can cancel these with this square. Right? I can also cancel this a1 square with this a1 square. Wow, I really simplified. I really simplified a lot. So 2 a1 a2 minus a0 a3. v2 square. Plus again here, okay, let me see if I can cancel something. A1, cancel this A3, cancel this. So what I really get is 2 times A1, A2 minus A0, A3. I have to keep this finally. A1, A3, A1, A3. A1, B3 minus B1, A3. That's what I get. So now I try to find the common denominator. Common denominator is two. I have 2 for sure. I have A0 here for sure, A1 here, and A3 here. I also have this bracket, A1, A2 minus A0, A3. That's a common denominator. Common denominator. Yeah. So the first term. The first term should be, I have here the common denominator is more than this, right? So I have A3 and the bracket. I have to move it upstairs. So A3, A1, A2 minus A0, A3, B1 squared. B1 squared. Plus A0, A1, A3, 2 squared. Plus. So actually, in this denominator, this denominator is the closest one to this common denominator. Actually, I have only A0 in addition to this. So this is A0, A1, B3 minus B1, A. Okay, that's what I get. So if you compare that with, hi, I have something missing. How come I have A1 there in the denominator, but there's no A1 here in the denominator? So, what's the problem? I trust myself better than this. You guys have notes with you? Maybe just, this is what you have in the note. Well, that's indeed so A1 is not there. Let's look at okay. Let's look at it. So I have these three terms in the denominator. The problem is that here I have this square of the bracket. Let's expand this square of the bracket. Expand this square of the bracket, then yeah, I run out of space, and maybe I erase this. I hope everything here is correct. So this goes to here. Maybe I even expand this bracket, so I get A1, A2, A3, B1 squared minus A0, A3, B1 squared again. Plus A0, A1, A3, B2 squared plus
A10 squared. Second term, that should be A0, A3 squared. 1 squared.
You're right. You're right. Yeah. Plus A0, expand this, A1 squared, B3 squared. The cross term is minus 2A A1, A3, B1, minus, no, plus, great. The last term is A0, B1 squared, A3 squared, A3 squared. Yeah, I see the trick here. So I think I'm correct. So this term and then this term are cancelled. So now you see that in all the other terms you have A1. So that's why you cancel the A1 in the bottom. So A1 actually disappears. So let's do this. Let's put the denominator here. So 2A0, A1, A3, A1, A3 minus now you see that indeed this A1 is common here in all the terms. So I cancel this A1, this A1, this A1, this A1, and this one. So I should get something exactly like that. Yeah. Is that right?
Yeah.
Yeah, indeed. That thing is correct. So you see, for third order signal, like the time signal, of course, you can also think it's a third order because the Laplace transform is third order. So this third order signal, you get two norms like this. Actually, two norms squared. First order, second order is simpler. I mean, you can derive these formulas yourself. If it goes higher, fourth order, then probably this formula becomes kind of messy. So probably we don't proceed. I just keep the you know the procedure, you know how to construct the Rouse table and the augmented Rouse table. Then you should be able to get that too. Of course, this kind of table is kind of a recursive computation. Informing the table. This is easy to be programmed. So in one of the homework problems, probably I ask you to program. Okay, finally, I have a few things. So, I think we have a look at this problem before. So I have a feedback system like this. You have a second order loop transfer function, and then close the loop, and then you are interested in this E. You want this E to be small, right? That's a E is a tracking error. So of course this E depends on this omega n and this zeta. Omega n you might just wanna you can normalize it, or you can you don't have to normalize it initially. You can just look at the expression and see what are the good values of E and zeta, so that this tracking error is small. I think a while ago, we looked at this problem, and we tried to obtain the time domain expressions of E. The time domain expression is like complicated with sine, cosine, exponential, all these things. Then you take the square, then you do the integration. Well, that's out of hand. Well, now let's use this frequency domain method. We might make it a bit simpler. What is E? E. So what is maybe we just ask this question. What is ES? Time Laplace transform of E. Laplace transform of E is the transfer function from here to there times the Laplace transform of R. Laplace transform of R is 1 over S, right? That's the step function. The transfer function from here to there, that's the sensitivity function. So that's actually 1 plus omega n squared s squared plus 2 zeta omega s times 1 over s. It's a Laplace transform of E. This is equal to s squared plus 2 zeta omega n s plus 2 then you have s squared plus 2 zeta omega n s. Then, so we again cancel this s with this s and this square. So that's the Laplace transform of ES. Or actually ET, little ET. This is ES is Laplace transform. So that thing is exactly the same. So basically, if we want to compute the two norm of ET, then we simply, we know the Laplace transform. If E is this, then we take that one. So the ET is simply inverse Laplace transform. This we need to compute two norms. Okay, what two norms? So this is the second order Laplace transform. So we have the formula in the previous page. So this is the second order thing. So then we see that ET, the two norm is equal to 2 norm squared. How about that? 2 norm squared. Is equal to 2A0, A1, A2. 2A0, A1, A2. So 2 times 2 zeta omega n q. So in the top you have A2 times B1 squared. A2 is this thing, omega n squared times B1 squared, that's 1, plus A0, that's 1, then B2 squared, that's 4 zeta squared, omega n squared. Okay, that's a 2 norm squared of the error. So this is equal to so I have omega n here, and omega q. So this is equal to 1 plus 4 zeta squared, 4 zeta omega n. So then you see that the 2 norm is a square root of that. Square root of that, then that's equal to this. What I do is that I take that omega n out the bracket, then I have this thing. 1 over 4 zeta plus zeta. So this is the 2 norm of E. I said that I want the 2 norm to be small. So you see that this omega n, the bigger, than this ET is smaller. So omega n, of course, that's a kind of this basically is inversely proportional to omega n square root of omega n. So that's not very interesting. You just why you say I increase the omega n to infinity, then of course you get to 0. But that's not realistic because omega n is the frequency of vibration. So omega n usually, is determined by other factors. It's probably let's think it's fixed. So omega n is fixed. then you know the ET, the true norm depends on this thing. So what's the best zeta? What's the best zeta? If zeta is a very small, damping ratio is very small, this term is very big. Not good. When zeta is big, when zeta is big, this term is big, again, it's no good. Must be like a kind of a intermediate value of theta, which is good. So what is the base zeta? The base zeta is of course the minimum value of this. You're just interested in the minimum of this. You know, try to find the zeta so that we minimize this. In order to find the minimum, we do the following. We do the derivative of this. We set the derivative to be 0. So the derivative is 4 zeta squared minus 1 plus 1. And then we set this to be 0. Right? So we set this to be 0, then 4 zeta squared has to be equal to 1. So zeta is actually half, right? Zeta, the best zeta is half. So you put a half in, then you get the minimum of this. So this is equal to 1 over 4 half, 4 times half, plus half. So this is equal to it's half plus half. That's 1. Yeah, that's 1. Yeah. So that they see that the second order feedback system like this, you can actually indeed have some sort of analytic analysis of this error and try to get to the best calculation. So here you look at the E. That's a property. You look at the two norm E. That's a property makes more sense. If you look at the trans function from R to Y, that's this. So the trans function from R to Y, that's this. What is the inverse Laplace transform of that? That's the impulse response from here to there, right? Inverse Laplace transform of the trans function is the impulse response. So if you look at the impulse response from here to there, and then compute the two norm, you follow the same this kind of it's a second order thing. You follow the same procedure, use the same formula, then you get this. From here, you see that in order to have a small impulse response, well, these things need to be big, zeta big. So you need a huge damping. So this kind of, if you try to analyze this, you don't really get anything that exciting and interesting. So here, omega n, you want it to be small. That's what does that mean? Omega n, you want it to be small, that means you want it to be slow, basically. So you want you want the system to be very, very, very slow. That makes some sense, you know. I mean, you have this system, you send the impulse, right? Basically, then that means you know, you look at the response here. If the system doesn't really respond that much, that means very, very, very slow. Then of course you don't have much response here. But then of course you get a small tunnel. That doesn't really guide us to any design trade-off or something. But still, you can explain the result. Okay. Okay. That's what we have here on two-norm computation. So today I spent the whole lecture on the computation of two-norm, time-domain two-norm. And the key in the computation is forming the augmented loss table from the coefficients. For simple Laplace transforms, second order, first order, or third order, you can actually get some kind of formula. Later on, you can directly use those formula in computation of two-norm. For higher order, you use a recursive computation. Yeah. So two-norm analysis of the system actually is very interesting. So for example, for this kind of thing, you can really get the relationship of two order of a relation of two-norm of error with the system parameters. And then you can analyze this and then get the understanding on what are the good parameters. Yeah? That's a whole idea. So that's the end of chapter 4. Chapter 4 is on time domain analysis. Time domain analysis, when we do time domain analysis, we need to do the transient analysis and the steady state analysis rather separately. Right? Transient analysis, that means you don't want to see overshoot, you don't want to see undershoot. If you have to see those things, you want them to be small, and you want to respond to be fast. All these things, these are called the transient behavior. Then you go to the steady state performance analysis. Steady state, of course, you want the steady state error to be small and things like that. All this analysis gives you some guidance in selecting your controller. For example, whether you need to put an integrator in your controller. Okay. Sometimes you need, sometimes you don't. Alright? So people always talk about PID control. Why you need the I? I is the integrator. So that's why sometimes you need to put the I in your controller. Then you have you need an I term in your controller. But you also hear people talk about PD control because they don't need the I. They need the just do PD. Well, that's because you don't need that. You don't need the integrator in your controller. See, these are all this kind of thing, right? Really gives kind of guidance in selecting the right controller when later on you're faced with a design problem. Another important topic is this overshoot issue. You see that sometimes when you control a system, if you use first you use 1 degree freedom control, you always get overshoot. But if you use 2 degree freedom control, you can avoid overshoot. So this kind of statement, I mean this kind of you make say this kind of discovery really helps you to determine the control structure, you know, and it gives a strong reason why 2-degree freedom control should be used when you do tracking controls. Okay. So after today's lecture, we'll have 3 more lectures. Of course, coming Monday, we're going to have a self-study. I'll keep you busy actually. I'll probably assign some programming things for you. For example, program the computation of 2 norm. So using MATLAB. Okay. We have 3 more lectures, and you know, I'm going to, of course, present something new. Then we all know the time for the final exam, right? I think it's in the middle of next month. Yeah. We are getting to the end. Good. I think I'll stop here today, and see you on Wednesday.